One day, the universe, as we know it at least, is going to end. And nearly 30 years ago, scientists reached a general consensus on our universe's most likely fate. It is that over trillions of years, its galaxies will drift farther and farther apart. Stars will cool off and die out. Black holes will slowly evaporate until all that's left is an infinite expanse of cold, dark space. This is the so-called Big Freeze. Powered by dark energy, it's a consequence of the accelerating expansion of our universe. By far the most likely outcome for the end of everything. Or so we thought. New, groundbreaking findings from the Dark Energy Spectroscopy Instrument, or DESI, may be uncovering a different story. It's found that dark energy's grip on our universe could be in fact weakening. But what does this mean? If true, and the cosmic engine that powers our universe is running out of steam, then the very fate of the universe hangs in the balance. And explore why dark energy may be running out of power. Could it be that all our cosmological models are wrong? Or is there another explanation? Let's travel back to 1998. At that point, we already knew that the universe was expanding, thanks to Edwin Hubble's observations almost 70 years earlier. But scientists were still attempting to pin down exactly how fast. In fact, many were wondering if the expansion would eventually slow down. Logically, this seemed to make sense. The tug of gravity should bring everything closer and closer together over time, right? Now, all of this could be solved by working out the Hubble constant, a value that represents the speed at which the universe is expanding right now. It can be measured in two ways, by studying patterns in the cosmic microwave background, or by looking at distant redshifts. By the way, scientists have found that these two methods don't produce the same results. However, we're going to concentrate on the redshift method. Historically, the redshift of Cepheid variable stars has been used for this, but type 1a supernovae also work well. And without knowing it, the astronomers studying these immense explosions were on the brink of a jaw-dropping discovery. We know how bright type 1a supernovae should be, because they all explode in pretty much the same way. Thermonuclear detonations of white dwarfs in binary systems. By comparing their true brightness to how dim they look from here on Earth, we can measure their distances. Then, by using the supernovae's redshift, the amount of light that has been stretched along its journey, we can determine how fast they're moving away from us, and therefore how fast the universe was expanding when their light was emitted. Easy enough, right? Well, when two independent teams of astronomers observed more than 50 type 1a supernovae, they found that the light appeared fainter than expected, which, although perhaps sounds trivial, turned out to be a pretty big deal. Teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that distant supernovae were dimmer because they were farther away than we expected. This was a huge revelation, as it came with a rather shocking consequence. It meant that the expansion of the universe was not slowing, but actually speeding up. Some unforeseen force was seemingly pushing entire galaxies apart. To visualize this, imagine if you took a marker pen and drew dots on the outside of an uninflated balloon. As you blow it up with air, the dots get farther and farther away from each other because the balloon itself, the space the dots reside in, is expanding in all directions. This unexpected result created more questions than it answered. A big one being, what is the force driving this acceleration? Unfortunately, the answer is still, we don't know. But it's been given the name dark energy, and most scientists think it's a property of the vacuum of space itself, the energy of empty space. Other scientists think it may be a type of energy fluid, or field that fills space, or even some kind of defect in the fabric of space-time, like one-dimensional wrinkles, so-called cosmic strings. And others think it may just be a flaw in our understanding of general relativity on the scale of the observable universe, and that the matter could be resolved without the need for dark energy at all. But whatever it is or isn't, dark energy presents a mystery that is intertwined with the accelerating expansion of the universe. This was such a monumental discovery that, following the 1998 finding, Rees, Perlmutter, and Schmidt, the three astronomers who led the investigations, were awarded the Nobel Prize in Physics for their work. This discovery of dark energy gave rise to a new model of cosmology, the lambda cold dark matter, or lambda CDM model. Lambda is a Greek letter that represents the cosmological constant. First postulated by Einstein, today it represents the mathematical parameters of dark energy. The other three letters, CDM, stand for cold dark matter. It's become what we today refer to as the standard model of cosmology, and it gives mathematical context to everything from the Big Bang to the future fate of our universe, and of course, all that happens in between. For decades, it's been the most widely accepted and most accurate model we have for the evolution of our cosmos. Confusingly, dark matter doesn't have anything to do with dark energy. We just use the word dark to describe two different things that we don't understand well. While dark energy is the force that's causing the universe to expand at an accelerating rate, dark matter is what we call the stuff in our universe that doesn't interact with the electromagnetic field. As in, it doesn't absorb or emit or interact at all with light. However, we believe it exists because we can observe its gravitational interaction within the universe, and the word cold in the model's name just refers to this dark matter having very little energy, since temperature can be thought of as a way to measure the energy of atoms. But if those two things make up the entire name of the model, the lambda cold dark matter model, what about everything we can see and do know about? It may not be reflected in the name, but it is captured within the model itself. Visible matter and radiation, including light, all belong to the category known as baryonic matter. Using independent measurements and observations, the scientific community has come to a consensus that under this standard model, about 68% of our universe is made up of dark energy, or this fundamental property of spacetime that we know very little about, with visible matter making up only about 5% and dark matter accounting for 27% of our universe. Let that sink in. 68% of our universe is made up of something we don't understand and can't measure directly. However, a crucial aspect of our standard model is that lambda, or dark energy, is assumed to be a constant. Almost every cosmological calculation relies on this being fact. It tells us that our universe has an ever-accelerating rate of expansion, and that it will therefore face a cold, lonely fate. Galaxies will continue to drift further apart as the space between everything expands. Stars will burn out, die, and cool off. All of the heat and energy in our universe will be spread impossibly thin over incomprehensible distances until the universe's final temperature hovers somewhere barely above absolute zero, ending in what astronomers call the Big Freeze. But what if we're wrong? For the first time since the discovery of dark energy, we may have uncovered one of its key properties, and it's not what astronomers expected. In 2024, the Dark Energy Survey released the largest ever sample of supernova results from a single survey, having studied the deaths of more than 1,500 stars. Initially, the data seemed in line with the idea that dark energy is constant, but when they combined the data with other results, like measurements from the cosmic microwave background and earlier galaxy surveys, something didn't quite add up. It was starting to look like dark energy might, in fact, change over time. If dark energy was proving to change, then scientists would need to change along with it. New mindsets would be needed, new ways of thinking about the mathematics to tackle the problems before them. Fortunately, when it comes to sharpening minds, there's the perfect tool out there for that. Brilliant, the sponsor of today's video. Brilliant is an online learning platform that can help you excel at maths, computer science, and more. It has these really engaging, visual, interactive problems that stretch you without being opaque. I had a lot of fun with this course on logic. I enjoy teasing my brain with the increasingly tricky puzzles, but you can also use it to reach serious learning goals, explore maths concepts until they make sense, or learn programming skills. And the best part is that it designs practice sets and reviews personalized for you, helping you learn at your pace. So if you're wanting to become a better thinker or problem solver to later prepare you to solve the mystery of dark energy, give it a try. Scan the QR code or click the link brilliant.org/astrum in the description to get started on Brilliant for free. You'll even get 20% off an annual premium subscription, giving you unlimited access to all Brilliant has to offer. Now, a changing dark energy is not what scientists expected to find, and it caused them a big problem. Although it was a promising result, there were uncertainties involved, so it was nowhere near being decisive proof. To find out the truth, astronomers needed a far bigger, more detailed map of the universe to test whether this hint was real. And for that, they turned to DESI. Installed on the 4-meter Mail telescope in Arizona, the Dark Energy Spectroscopic Instrument is charting the optical spectra of tens of millions of galaxies and quasars across billions of years of cosmic history with one mission: to test whether or not dark energy is constant. Able to capture light from 5,000 galaxies simultaneously, DESI is measuring the position and receding velocity of some 40 million galaxies in order to accurately measure the expansion history of the universe over the past 11 billion years. This is a truly international effort, involving more than 900 researchers from more than 70 institutions around the world. And in 2025, the first major datasets were released. They included results from the first 3 years of the survey, with 2 more to go. And what they show is nothing short of extraordinary. DESI used data from nearly 15 million galaxies to build the largest 3-dimensional map of the universe ever created. This 3D map lets us fly through millions of galaxies, each containing 200 to 300 billion stars. Earth is at the center of this animation, and every dot is an entire galaxy. The blue represents farther galaxies from us, while the white shows closer objects. In other words, this map is almost unfathomably dense with galaxies. Using this data, a team of astronomers have measured baryon acoustic oscillations, or BAOs, from more than 14 million galaxies and quasars. BAOs are basically the fossilized echoes of sound waves from the early universe. By tracking how they change in size across cosmic time, researchers can work out exactly how fast the universe was expanding at any given moment. Here, the lighter blue color represents sound waves rippling through the primordial cosmic sea of our early universe. Over time, those slight variations froze in place, carrying with them a slightly more dense collection of matter. Over hundreds of millions of years, those waves would gather more and more material, eventually becoming stars and galaxies. These waves are still visible today in the form of the cosmic web. The researchers then combined this DESI data with other measurements, like the microwave radiation left over from the dawn of the universe, known as the cosmic microwave background, supernovae redshifts, and weak gravitational lensing, or how the light from distant galaxies warps due to gravity. And what they found added more weight to the 2024 discovery. Not only does it look like dark energy's influence is changing, but it's potentially decreasing over time. In fact, they found that dark energy's push may have weakened by roughly 10% in the last 4.5 billion years. You can think of it kind of like a foot still on the gas pedal but gently lifting, which means that the car is still accelerating but at a slower rate than before. Likewise, the expansion of our universe is still accelerating, but not quite as rapidly as it was a few billion years ago. And if dark energy is evolving, rather than remaining constant, then our standard model of cosmology is missing something, and something big. Assuming this model-shattering discovery is correct, it could mean a very different future for our cosmos. Instead of a big freeze where our universe expands forever, leaving us with a cold, dark, lonely end, we may end up experiencing an alternative reality. If dark energy's influence continues to weaken over time, decreasing until it becomes negative, then eventually expansion of our universe could stop altogether. Instead of a big freeze, it would end in a much more violent cataclysm. Imagine the raw power of the Big Bang, exploding and expanding out with enough energy, heat, and matter to form all the galaxies and stars across our universe. And now, imagine the exact opposite of that. A reverse Big Bang, where everything changes direction and rushes in toward a single point, with enough intensity to undo everything that ever existed in one cosmically colossal big crunch. I've spoken before about the possibility of a big crunch, as well as other theories about how physics gets weird at the end. Even more important to us, impact. It means our current model of cosmology is incomplete. It could mean that the theory of general relativity needs modification too, and that there's more to learn about particle physics, possibly involving new fields or forces. But before we rewrite any textbooks, we have to be sure. And right now we're close, but we're not quite there. Sigma, or standard deviation, is the way scientists measure confidence. The higher the sigma, the less likely a result is due to random chance. And in the chase for evolving dark energy, those sigma levels have been climbing. On its own, DESI data lands us just above 2 sigma, which is about 95% confidence. Interesting, but nothing you'd bet your career on. Combine DESI with other instruments and the number rises past 3 sigma. even brushing the 4.2 sigma mark in some combinations, roughly 99.997% confidence. While this is considered to be strong evidence, meaning that the result was unlikely due to random chance, it's still not quite at the level physicists require for it to be considered a solid discovery. For example, other evidence with this confidence level has turned out to be false before, so physicists typically wait for even clearer results before claiming a new discovery. The gold standard in physics comes when confidence reaches 99.99994%, which is sigma 5. And even then, things can still be wrong. For example, in 2011, physicists at the Gran Sasso laboratory in Italy measured some neutrinos arriving a few nanoseconds early, a feat that would require the particles to have traveled faster than the speed of light, breaking the cosmic speed limit. They reported a confidence level of 6 sigma, even more impressive than the gold standard for new discoveries. To put that into perspective, barring any unexpected mistakes in the experiment, 5 sigma represents about a 1 in 1.7 million chance of the result being a fluke, and 6 sigma is more like a 1 in 500 million chance of the result being wrong. So this was quite an astonishing observation, and it made headlines around the globe. Unfortunately, it was later revealed that the physics-breaking observation had actually been due to a faulty fiber optic cable and clock synchronization error rather than neutrinos breaking the laws of physics. Needless to say, there's still a little way to go with the concept of evolving dark energy. Now in its 4th year of the 5-year survey, DESI is well on its way to having measured 50 million galaxies and quasars, continuing to offer valuable data in the quest to understand dark energy. But it's not our only tool. Over the next few years, new experiments will be conducted. Other missions will further the exploration of the nature of dark energy, and complementary datasets will come out for analysis. The European Space Agency's Euclid and NASA's Nancy Grace Roman Space Telescope will extend measurements across even larger volumes of space and at higher redshifts. And the Vera C. Rubin Observatory will scan the sky for millions of supernovae, providing the enormous dataset needed to hopefully bring us to the 5 sigma mark. I personally can't wait to see what they find. But in the meantime, the new DESI findings are tantalizing and bring us to the precipice of a whole new view of both our standard model of cosmic evolution and the ultimate fate of our universe. Let me know in the comments what you think. Will the universe end in a big freeze? Or is a big crunch on its way? What ending or rebirth do you imagine for our universe? There's a reason these educational mini documentaries are free for everyone. It's not just the ads or sponsors, but it's thanks to our hundreds of Patreon members who make it possible for everyone to get the best possible content. They are the foundation that keeps Astrum steady and focused on quality over clicks. Every video you watch exists because there's a community behind it that values learning and curiosity. If you'd like to be part of that group, the people who keep space education open to everyone, join us on Patreon through the link below. We would love to have you.